Okay, today we're going to look at a technique called implicit differentiation. To introduce this topic, let's consider the circle with the equation x squared plus y squared equals 25. Recall that this is a circle where the origin is the center and you would have a radius of 5. Okay, so imagine drawing this with a radius of 5. We're trying to find the slope of the tangent line at the point 4, 3. So let's say this is our point on the circle, 4, 3. Notice if you do 4 squared plus 3 squared, you get 16 plus 9, which is 25. That confirms that that point is on that circle. So we're trying to find the slope of the tangent line going through that point. So if we were to do this using traditional means, we would have to find a derivative of our function. Well, the problem is this isn't a function. If you look at the graph here, clearly it would fail the vertical line test. But suppose we tried it anyway. All right, let's try to get y alone. So y squared would equal 25 minus x squared, and then y would equal plus or minus the square root of 25 minus x squared. If I were to then find my derivative, y prime, okay, we know that this is really a quantity raised to the 1/2. So, well, let's carry along that plus or minus. So that 1/2 would go down in front. I'd have 25 minus x squared to the negative 1/2. And then I would chain along a negative 2x. And if I clean this up, keeping my plus or minus there, the 1/2 and the 2 will go to 1. I'm left with negative x all over. I could turn this into the square root of 25 minus x squared. So this is in terms of x. If I were to take my x value of interest, which is 4, and put 4 into this, all right, so my slope at x equals 4, well, that would give me plus or minus negative 4 all over. In the bottom here, 25 minus 4 squared, that's 25 minus 16, which is the square root of 9, which is 3. So the problem with this is we have more than one answer. Okay, so it says here we have a plus or minus in our derivative. Which one is it? Well, we can see from our graph that 4, 3, all right, if we were to look at the tangent of that, it'd have to have a negative slope. So in this case, we know it's going to be negative 4 over 3 for our slope. But most of the time, you're not going to be able to draw a graph like that. We're not going to know what it looks like. So we're going to introduce a technique called implicit differentiation. Now, all of the differentiation we've been doing to this point has technically been known as explicit differentiation. Okay? The bottom line with explicit differentiation is that we were dealing with functions. When we look at a technique called implicit differentiation, this is going to be dealing with non-functions. All right, and what that generally means is that you're going to have x's and y's in the problem. So we're going to redo this using a technique called implicit differentiation. So the idea is if you have an x term or a constant term, you're going to just take your normal derivative using your normal rules as you know it. So you're just going to work left to right. So the derivative of x squared is 2x. So notice in this technique we do not need to get anything in y equals form. We're just going to work from left to right. So the derivative of x squared is 2x. Okay. Now for the y term, this is where it gets a little bit tricky. The derivative of y squared is 2y, and we say that we're going to tack on a dy dx. Okay, so it looks like multiplication. All right, we're taking a derivative of y with respect to x. Okay, and then I'm going to carry along my equal sign. The derivative of 25 is 0. So what we're going to do now is we're going to solve for dy dx. So I could subtract over my 2x. So I have 2y dy dx. is equal to negative 2x. And then our goal is to always get dy dx alone. Okay, so if I were to solve for this, I would divide over my 2y, and my answer would be negative x over y. So dy dx represents the derivative. All right, and notice your answer has an x and a y in it. All right, this is because it's not a function that we're talking about, so you can expect to have x's and y's in it. So the bottom line is you just need to remember, if you're taking the derivative of a y term, you have to tack on a dy dx. Okay, let's look at, and if you look down here, they're showing you that technically when we take the derivative of 2x, all right, it's really dx dx, or we're finding the derivative with respect to x. So you can kind of think of this as dx over dx. Well, anything divided by itself is 1, so we don't bother to write it. So it's really saying we're taking the derivative of a term with respect to x, whereas right next to it we're taking the derivative of a y term, okay? But we want to do this with respect to x, so we're just going to tack on a dy dx. Okay? So let's look at some examples. We're looking to find the derivative, dy dx, for this equation at this particular point. So to do this, we're going to work left to right. The derivative of x squared is 2x. Because it's an x term, we don't have to tack on anything. It's technically dx with respect to x, but we're not going to bother to write that. Okay? Minus 2y dy dx. So if you're taking the derivative of something with a y in it, you have to tack on a dy dx. The derivative of 16 is just 0, so we have equals 0. So from there, our goal is to solve for dy dx. Okay? So negative 2y dy dx is equal to negative 2x, just like the last problem. Except this time, you divide over your negative 2y, and you're going to get positive x over y. Now this is what our derivative is equal to, okay? But if we want to find the derivative at the point 5, negative 3, I need to plug in. So dy dx at 5, negative 3 would equal, so notice my notation here, okay, something as simple as just using the at symbol and then at that point, it would be 5 over negative 3. So this would be the slope of my tangent line. Alright, so the slope of my tangent line is found. So the dy dx just represents a derivative just like before, but the only difference is you're going to have an x and a y in it. Because we want to find the derivative at a specific point, we're plugging in the x and the y value into it. Okay, let's look at one more. Now this one is a little more complicated because we see an x times y. So guess what that means? We need to use our product rule. So we really have x times y. So we have two functions there. So the derivative of x is 1. I don't have to tack on anything. So after that we would have our y as is. So the derivative of x is just 1, and then we have our y as is. Plus, now we're going to keep x the same, and we need to multiply by the derivative of y. Well, the derivative of y is 1, but it's a y term, so we need a dy dx on the end. Plus, now that's just my product rule, that's just the x times y piece. Then we have a plus y in the problem. Well, the derivative of y is again 1, and then dy dx. You don't really need the 1 there, okay, but I like to show it in the beginning. Equals, and then the derivative of 8 is 0. So we're trying to find the derivative at the point 2, 3. So one option is you can solve for dy dx, okay? So if we were to do that, let's subtract over the y. So I have x dy dx. I'm going to keep my dy dx terms on one side. So I have x dy dx plus, so I'm looking at this term and this term, and I'm going to subtract over my y term. Okay? So if I'm going to get just one dy dx to show up, I could factor it out as a GCF. If I do that, I'm left with x plus 1 on that side equals negative y. And then from there, dy dx would equal negative y over x plus 1. Now the problem wants me to find the derivative at the point 2, 3. Okay, so let me give myself some more room here. At the point 2, 3, so dy dx at 2, 3, well, I'm going to plug in 2 for x and 3 for y, so this would be negative 3 over 2 plus 1, so negative 3 over 3, so negative 1 would be my answer. The other way you can get that, suppose you didn't want to solve for dy dx. If you go back to our original answer up here, all right, look at this line right here, all the way to the 0. If you were to just plug in right from there, so or, watch what happens if we were to plug in 2 for x and 3 for y right away. So 3 is the y value, plus I have the x value of 2 times the dy dx, plus another dy dx in the problem, and then equals 0. So now from there, these are like terms that I can combine. So I have 3 plus, I really have 2 dy dx's plus 1 more, so that's going to give me 3 dy dx's equals 0. Well, from there, if I were to solve for dy dx at that particular point of 2, 3, which I plugged in for, notice I would get dy dx equals negative 3 over 3, which is negative 1, which of course matches what we have up there. So the idea is sometimes the question may want you to solve for dy dx, all right, which we did down here. Okay. Other times, if it wants you to find it at the point, such as 2, 3, you just go ahead and you plug in, get your answer, and you're done. So if it's multiple choice, you're looking for negative 1. Okay, so you don't have to always solve for dy dx. You can plug in right away if you want. Bye-bye.